For decades, humanity has pointed its instruments at the night sky, hoping to catch a whisper from the void. We've mapped billions of stars, yet the cosmos remains quiet. To search for extraterrestrial intelligence, scientists rely on massive arrays of radio telescopes, scanning deep space for artificial transmissions. The prevailing strategy assumes an advanced civilization would broadcast a specific type of signature. Researchers specifically look for incredibly narrow, highly concentrated spikes in radio frequencies. The logic here is straightforward. Natural cosmic background noise fluctuates constantly, but it doesn't produce perfectly sharp, solitary radio spikes. A signal like that stands out as the calling card of advanced alien hardware. But a recent study from the SETI Institute points out a flaw in this assumption. It asks a critical question. What happens if a civilization broadcasts a perfectly sharp signal, but that signal physically changes shape before it even leaves its home system? If that is the case, our highly specialized search algorithms are acting as a blindfold, inadvertently filtering out the exact messages we've spent decades waiting to hear. Scientists already account for how radio waves degrade as they cross the millions of light years of interstellar space. But until recently, they overlooked the extreme environment immediately surrounding the alien transmitter itself. An alien civilization transmits a sharp, concentrated, narrow-band radio signal. But before that signal can leave its solar system, it passes through its host star's turbulent environment, hitting a wall of constant stellar winds and fluctuating plasma. Extreme space weather events like a coronal mass ejection can erupt from the star, slamming directly into the escaping radio wave. When these extreme fluctuations hit the transmission, the concentrated energy of the narrow signal is forcefully smeared across a broader range of frequencies, stripping away its original structure. The radio wave survives the collision, but its shape is permanently altered. The structural degradation severely weakens the sharp, identifiable peak that our current detection methods rely on to trigger an alert. The signal's most destructive encounter happens mere inches from the transmitter, where the violent gauntlet of its own sun poses a far greater threat than the millions of light-years of empty space ahead. Proving this theory presented a logistical hurdle. Researchers cannot fly measuring instruments to a distant star system to observe this plasma interference firsthand, so scientists found a workaround. They utilized human spacecraft already operating within our own solar system as a local, measurable proxy. Probes in our solar system send narrow-band radio signals to Earth. As they navigate the sun's turbulent environment, these communications interact with local space weather. Tracking these transmissions, the team calculated the exact degree to which our sun's plasma density and solar winds distorted the spacecraft's signals. They took this local data and applied it to a variety of stellar environments. This allowed them to build a robust mathematical framework to estimate the level of signal broadening around any star. Observing the interference from our own sun provided the exact diagnostic tool needed to map out the invisible degradation of signals across the entire galaxy. With this framework established, the researchers shifted their focus from our local sun to the billions of potential targets scattered throughout the Milky Way. They quickly identified a primary antagonist in the search for extraterrestrial intelligence: M-dwarf stars. This chart shows the distribution of stars in our galaxy. M-dwarfs absolutely dominate the visual space, making up roughly 75% of all stars in the Milky Way. The physical hazard of M-dwarfs is their extreme volatility. They possess highly active space weather environments with intense plasma winds that are incredibly efficient at capturing and broadening narrowband radio signals. This means the vast majority of potentially habitable planets orbit stars surrounded by an inescapable barrier. These volatile stars effectively erase traditional technosignatures before they even leave the system. This physical reality directly addresses the radio silence SETI has experienced over the past several decades. Because our observation hardware and software are strictly optimized to flag sharp, concentrated spikes, these broadened alien signals slip completely below our detection thresholds. The great silence we hear might not indicate an empty universe. It could simply be a persistent hardware and software bias filtering out the exact data we should be analyzing. To correct this blind spot, future SETI programs and target selections have to cast a wider net. Search arrays must be recalibrated. Instead of relying solely on ultra-narrow spikes, our systems need to remain sensitive to the wider, fainter signatures produced by stellar interference. To finally answer whether we are alone, we cannot just look for the pristine transmission an alien civilization might broadcast. We have to tune our instruments to the battered, broadened reality of what actually survives the journey to Earth.